All right, so that's actually good. All right, my friends. I want to focus momentarily on when we're wrong, because we can be wrong. These tests they're probability tests, so you can be wrong in your conclusion, and I just want you pretty much to be able to know that and how to measure it when it's easy to measure. And sometimes it is easy to measure. So let's go back. If you get a small p-value, so that was that p less than 5%. What does that mean? What does that mean when you get a small p-value? Good. You found an outlier on the null curve, which means your result doesn't belong on the null curve, so it most likely belongs on a different curve, which is technically your research curve. Awesome. So that's the belief. You say something changed. If something changed, you're off the null curve, you're off that blue confidence interval, and you're into some other curve somewhere else. Most likely. But of course you could be wrong. What's the chance? We know this. The chance that we're wrong is 5%. Absolutely. The chance that we're wrong is 5%. And it's only 5% because we've made it be that way. We've made the decision that 5% is the cutoff. So we've said that z-score, which we'll get to momentarily, that z-score right there is the cutoff for unusual. So anything past 5% is too small to believe the null, so we believe the research. We could be wrong. I want to focus on what that's called. It's called a type 1 error. Okay? It's also a false positive. We used that term back in the day, back in 243, false positive. Now, it seems kind of weird. Why is it called a positive test result? You say, Jerry, go ahead. Because you're saying, yes, something changed. So in other words, think about going to the doctor and taking a test. Like I had Lyme disease like a half a dozen times, right? I go to the doctor, I take a test for Lyme, and it comes back positive. That means something changed. I didn't have Lyme disease, and now I do, or at least the test is saying I do. I'm sorry, Christian, I had it. He's living on the East Coast, it's rough. I'm working in the woods, it's rough. So basically, it means something changed. The status quo is you don't have Lyme disease. You take a positive test result that says you do, so something changed. Yeah, make sense? Okay, good. So, what's that?
I'm sorry, I was making a smart comment.
That's okay.
I said lifestyle choices. I thought it was funny.
Exactly. Yeah, lots of positive test results. Many positive test results, right? All of them mean something changed, right? You have it in your system, or excuse me, you assume you don't have it in your system. You take the test, boom, you do. That's a positive test result. So anything that changes from status quo. And the chance of it being wrong is called, I don't know if you can see this right here, that's a Greek letter alpha. That's a Greek letter alpha down there. It's on your little handouts too. So that's the symbol that is used in general. The symbol that is used is Greek lowercase alpha. Capital alpha is a big capital A. So a lowercase alpha is called the significance level. It's generally set at 5%, which corresponds to, of course, as Paris said earlier, 95% confidence. So you're building a 95% confidence interval, which means you've got a 5% outside the interval significance. Confidence, significance, add to 100%. So we're testing, when you see a significance of 5%, you're assuming a 95% interval. Cool? It's called a false positive, or more classically, it's called a type 1 error. Type 1 error. Cool? Good so far. Now, this is where we could have made a type 1 error in this most recent study. We made the conclusion that from 0 to 1 hour, which is the time that they're in the restaurant inhaling the smoke, lung function parameters were reduced. Can you see why that's a positive test? Why that's a positive test result? Why that would be a positive test result? What were we assuming? When you go over the study, we assume that they're not reduced, that they're not decreased, and then the test showed that they appear to be decreased. So that's positively saying, yes, something changed. We were expecting it not to decrease, but the data says it did decrease. That's why it's a positive test. I know it seems weird to call it positive because they decreased. Positive test results just means it shifted from null. Null says they don't decrease. Data says they do. That's a shift away from what you were expecting. Christian?
So it's greater than 5%. Is that like an acceptable amount of decrease?
Yes. No. Yeah. Well, it's either some amount of decrease, no decrease, or an increase.
Okay. It's hard to visualize.
I know it is, and that's the margin of error playing with your mind right there. Let's come back to that if you don't mind. I got a great example. Your card trick from the first day that'll. Christian asked a fantastic question. Is greater than 5% like acceptable decrease? It can be. It can also be you haven't changed at all, or you change so much that it's off the chart that way. So basically, greater than 5% means you didn't significantly decrease. Everything else is kind of looped up in that. But we'll come back to that with the card trick, I think. Cool? Very good question. So basically, yeah, this is a positive test result. We said something changed. That's what makes it positive. We said lung function parameters went down. That's a positive test result. Not positive like, yay. Positive like something different. And we could be wrong, of course, how often again? How often? 5% of the time. So if we ran this test 20 times, 1 out of those 20 is going to be a wrong result with small p-values. Okay? Let's talk about it in context. I already verbalized this once before. So I'll get you set. I'll get you started. Oh, Susie, go ahead.
Sorry, I'm just trying to get this. So a positive test result means that it changed from what you were testing in the null hypothesis.
Exactly. You said it perfectly. A positive test result is not necessarily a good thing. It's like the binomial. We talk about success probability. Success might be getting cancer, but it's what you're interested in studying. So we were studying lung function parameter. The null said it didn't change. If it changes significantly, that's a positive test result. Yeah, very good, very good, very good. So I'm going to get you started on how to verbalize this. We're going to define this error in context. We said that lung function parameters were decreased from 0 to 1 hour, comma, when in fact, what? If we're wrong, we said they decreased.
Not the increased.
Don't say increased.
Oh, shoot, I know.
When in fact they didn't.
Did not.
Yeah, you don't have to overstate. Right. So we made the claim. We made this claim right here. We made the claim that lung function parameters were reduced. They decreased, they went down. If we're wrong, they stayed the same or increased. They didn't decrease. That's contextually defining a type 1 error. We said, and you're going to make this, if you get a p-value less than 5%, you're going to say this. That's the point. You get a p-value less than 5%, your data landed out here in the tail. Yeah, something changed. Something changed, for sure. But you have to admit the fact that you could be wrong. And the way you could be wrong is, we make this claim that lung function went down when it might not have. It might not have gone down. I'm not saying to fixate on the error. You can't fixate on it like, oh my God, I'm doing a hypothesis test again. Don't say that. Just make sure you realize that exists, that possibility exists. Go ahead, Karen.
No, well, I was just thinking, would it work if we said to this effect, lung function did change when we stated it would not?
I like that. I like that. The only problem is it focuses on the sample too much compared to the population. And this is a minor point. I wouldn't be picky about this in this class for sure. But realize what a hypothesis test is doing. You're drawing a sample to actually study the entire population. So it's better to speak of it in terms of when you say lung function decreased in our sample, or you didn't say sample, I know, but you were. So just say lung function parameters have decreased in the general population, but in fact, we may be wrong and they may not have decreased. So basically, just as long as you're implying your population, I'm a happy guy.
Okay. And
so will the research journals as you read/write them. Is that, go ahead, Ken.
Why can't you say I'm 95% confident?
You can.
That, oh, okay.
You absolutely can. That's actually the more formal. There's all kinds of formal ways to make these statements. This would be called a rejection of the null hypothesis. I don't have you guys use that language too much in this class because it's too. The way I like to think of it is explain this to your neighbor as you're out trimming your hedge on a beautiful summer day. And did you read that article about aspirin? How it makes your toenails fall out? I'm 95% confident that the null hypothesis has been rejected. I mean, it's one of those things like your neighbor's not going to understand that. Right? But if you can say it appears that taking aspirin at too great a doses makes your toenails fall out. And then you can draw a little picture and kind of explain why. But I like to get away from the formal statements, but it's implied. So you don't have to say it, Ken. It's going to be implied in our results. If you tell me the p-value is less than 5%, I'm immediately assuming you're saying that you're 95% confident in your result. Is that fair? So you don't have to say it. Of course you can say it. Of course you can if you want to.
So I was right to say that to the video because I...
Oh, dude, Ken. Hell yeah. Totally. Totally just say that to the video. All you out there listening. Yeah, you're completely correct. You could also say, we reject the null hypothesis. Now think about why that makes sense. We've rejected the null hypothesis here. right? We have, because the null hypothesis said what? It does not decrease. We're rejecting that, and we're supporting the research hypothesis. But I like to kind of just throw that language out and just say it in English. It appears lung function parameters went down. That makes more sense. You can explain that to your neighbor. They understand coughing. Maybe not a null hypothesis and rejection of such. Fair enough? So, this is the way we could be wrong, and we just defined it. We said they went down. Well, maybe we're wrong. Maybe they didn't. We're 95% confident, not 100% confident. Is that fair? Good, 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 good. Very good, very good, very good. Let's go the other side of the coin. Large p-value. That's why I love the secondhand smoke article, because it has one of each in there. Large p-value. Large p-value. Nothing changed. Therefore, it's what kind of a test result if nothing changed? Careful, nothing changed. It's a negative test result. You were expecting not to have Lyme disease, and the test came back negative in this case. Right. And this, well, for me, yes. Yeah, that was a safe bet for me, actually. Does Sean have Lyme? Yes, probably, because he always seems to have it. But that's what a negative test result means. You were expecting not to have Lyme disease. You're expecting not to have too much alcohol in your system. And the test came back saying, you're right. There's a negative test because there's no presence of what you're studying. So there's no presence of decreased lung function. After 3 hours, let's go to this. Here's a question. What's the chance that you're wrong? It's a loaded question. It's a loaded question. You can't answer it yet. And we're going to see why here in a second, okay, friends? We're going to see why in a second with the drawing. It's a false negative. False negative. False negative just means that you said nothing changed, but it may have changed. That's the whole thing. It may have changed, but you missed it, right? There may have changed, but you missed it. And we'll see how that works with a picture momentarily. It's called a type 2 error, which is also called Greek letter beta. Greek letter beta is the symbol for it. Okay, we're going to come back to this with the context of our card game from that first day of class here momentarily. So in context, we could have made this error here. Here's where we could have made a type 2 error. Can you see why this is a potential type 2 error? Give me one reason why this is a potential type 2 error. Remember that type 2 is false negative. What's the claim we're making right here?
Nothing changed.
No, we're claiming, what was in the null hypothesis for this one?
Same thing.
The same exact thing, which was lung function parameters do not decrease. Are we disagreeing with that, with the statement? No, we're actually supporting that. So there's a couple different ways you can say that formally. You could say that I failed to reject the null hypothesis. That's the classical way of saying it. We failed to reject the null hypothesis. You can say that if you want to. I don't say it too often in this class. You could say you support the null hypothesis. That's also fine. My personal favorite is to say it in English. After 3 hours, or at 3 hours, most lung function parameters were not reduced. Basically, you're restating the null hypothesis, saying, yeah, I believe this one. I believe this one up here. So therefore, they're not reduced. Bigger than 5%. So in context, I'll get you started. And they always have a comma. We said lung function parameters were not reduced, comma, when in fact, remember, we're wrong. We said they weren't reduced. How could we be wrong? If they actually were. That's how we could be wrong. That's a false negative. That's like saying, Sean, take the test for Lyme disease. Okay, boom, it came back negative. Sweet, I'm Lyme-free. Except, I might not be. That test could have a false negative. We talked about this in 243 at the very last project. False positives, false negatives. This could be a false negative, a type 2, because you said everything's fine, but it might not be. You might not be fine. What's the chance of this? Careful. 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 You don't know yet. Here's why. Can I draw a picture to explain why? This is not a simple idea, and we're going to hold off on the computation for a while. I think it's important to know how to compute it, but it's also important to know at this point why it's so hard to compute. Okay, so we're going to come back to this graphic as we go on in this class, but for right now, we're going to draw, I'm trying to put a marker in my pocket. Here's your null curve. Your null curve. Can I call it that? Is that okay, friends? Null curve. Get used to this, because we're going to use these all the time. It's one of your TI draws. It's just a very, very helpful very helpful kind of a graphic. Null curve. What's right here? Beautiful. 0 bobs per liter, whatever it is. It's the baseline lung function. Okay, so from 0 to 3 hours, we got a little 5% cutoff here. That's pretty important. I got a 5% cutoff right there. Red. All right. So, there's right here. If we land in this part of the curve, we get a big p-value. We get a big p-value. So what are we going to say if we get a big p-value? You can say it in general, or you can say it with the specifics from this particular experiment. But if we land in the blue part of this curve, what's the overriding decision? P-value is bigger than 5%. So what we were studying, who do we believe? We got an H0, we got an H1. If we land here, big p-value, we believe H0. Because there's no reason not to believe H0. So if you land here, let's put that in here. You believe, let's put purple. You believe H0. Simply put, there's no reason not to. And this goes back to Christian, your question, which was awesome. I told you I'd get back to it. You said, okay, so if your p-value is bigger than 5%, does that mean that it didn't decrease significantly? Yes, that's if you're landing like over here. It decreased, but not statistically significantly. If you land closer to here, there's like almost no decrease, it's almost the same. If you landed over here, it's like an increase, but not a significant increase. And if you land way over here, it's a wickedly significant increase. But in this test that we were just doing, we were testing to see if there was a decrease, not an increase, which goes back to Ashley's question about 2.5 and 2.5. If you were testing just for a change, you'd put 2.5 in both tails. Now you wouldn't put 5 in both tails. I mean, you could put 5 in both tails, couldn't you? But your confidence would then be what? 90%. Nice, guys. Awesome. We try to keep it 95%, and you will see why as we go on this class, why we like 95% versus other numbers. Because it seems like why not go to 99? You're about to see why. 99, 98, and things like that. Going more isn't always a good thing. There's 2 ways to be wrong. Now, we could be wrong here, correct? Because if we land down here, put it in orange, if we land down here, we believe H what? What do we believe? Yes, we believe H1. And we're going to spend most of our lives in this class on this curve. Because we know where this curve is. We know what baseline looks like. But here's the deal. The reason we could be wrong, we could be wrong no matter where we land. If we land here, we're going to believe H0. Well, that could be wrong because H1 might be correct. Remember? H1 might be. You never know which one's right. What you're doing is you're measuring shades of gray. It's not black and white. It never has been in this class, has it? It never has been. It's a bastard class. It's never black and white. It's shades of gray. So what you're doing is you're using that p-value to tell you which of these two is more likely based on your data. So if you land over here, it's more likely that this guy is correct. So you fail to reject him, i.e. you support him, you believe him. If you land over here, it's more likely this guy looks correct because it's more likely that guy is incorrect. So you reject him and you go with him. But here's the deal, and this is why it's so hard to measure type 2 error. Let me draw another curve, which I'm going to call the research curve. So the null curve's here. I'm going to put the research curve down here. Okay? We drew the null curve assuming that lung function parameters actually didn't get decreased. But what if they do? If they do, there's going to be a curve down here to the left, isn't there? Now, I'm not drawing this on top of the same line as this one, but please realize these horizontals represent the same thing. They're both lung function. I would put it up on top of here, but it gets in the way of what's up there too. So please realize both of these horizontals are lung function. So you got lung function here, you got lung function here, and you've got lung function here. But realize that 0 here is 0 here as well, okay? You can bring that 0 all the way down if you want to. And I am just randomly placing this here. The important thing is that it's to the left of the other one. What does that mean about lung function on this curve? It's decreased with respect to the null curve. And that's why I'm calling it the research curve, because this is, if you will, the H1 curve. This is the curve that's describing the decrease in lung function. Where's the center of this? Here's the best trick question of the day so far. What's this? Be as specific as you can about what that value equals.
Negative z-squared?
It's got to be negative. That's the best answer. How negative? We don't know. We don't know how negative. We can put a 0 here because that's baseline. How far below baseline is this? All I know is it's negative. That's all I know, is that that number is negative. All I know is that number is negative. That's all I know. Bob, go ahead.
But you would know that number if you had the data.
Careful.
Wouldn't you?
When we have the data, we land on this curve.
Right.
So here's the deal. Here's the deal. Here's the deal. We were using the red asterisk for significance working. So when we ran 0 to 1 hour, 0 to 1 hour, we said, yes, lung function is decreased. And we added that asterisk somewhere around here. Somewhere around here. Now, see if that makes sense as to why it makes more sense to believe this curve. If we land here on this curve, we're only that high. But if we land there on this curve, we're much higher. So therefore, it's much more likely that we're on this curve than we're on this curve. Does that make sense?
Yeah.
I still don't know where that center is. But I know the height of the curve is going to be higher for that data point on this curve. Now, unless, of course, this curve is way the hell down here. But if this curve is way the hell down here, that test statistic is most likely going to land way the hell down there too. Remember what it means. I'll get your question in a minute, Christian. I'm sure it's going to be a good one. If there is a really, and I'm saying wickedly significant decrease, this curve won't be as close to this. And I'm using close in a very subjective way here. This curve is going to be way, way down here. But if that's the case, chances are we're not going to land this close to 5%. It's going to be off the charts low. Still more likely on this curve. Does that kind of answer your question, Bob?
Yeah.
Are you sure?
I think so.
You're getting keep thinking if you want to phrase it a different way. This is very important to understand. Christian, go.
So does that 0 represent data, or does it just represent the baseline?
It's the baseline average of the population.
So it's not really 0, it's just a symbol of the
Oh,
baseline.
brother, it's never 0. 0 is the normalized value of it. So your baseline population has a unit. It's milligrams per deciliter, beats per minute, range of motion in a joint. It's all these things. But because all those things have their own curves, we make one standard normal curve and put 0 in the middle of it. And we can make everything fit that curve. Fair? Great question, great question, great question. This curve, we don't know where it is. All we know is it follows the research hypothesis. This guy here follows the null. He follows the null. This guy down here follows the research. The reason why I can say this is centered on 0 is because we have the baseline measurement. I can't say where this is centered on this one. All I know is it's down from the baseline somewhere. And it's still a bell curve because it's the whole central limit theorem. Fair? Fair? Paris, go ahead.
So if they say like if they say the p-value,
Yes.
they're talking about null.
Yeah, absolutely. Your p-value is always based on area of the null curve. Because the p-value can't be based on the area of this, because the only reason you can calculate a p-value is because you know where this is. Think it's the normal. Think it's the normal. Whenever you guys ran the normal in 243, you guys had Donna for 243, you did areas under the bell curve with the little charts in the back of the book. Those charts had a center at 0 and a standard deviation of 1. You have to know that in order for those areas to actually work. You don't know what the center is on this one. So you can't do the p-values off of this. Unless we supply a center. And that's what I do not want to do right now. We'll get into that in about 2 weeks. Because I do want you to understand what's going on with this curve. But I don't want you to get overly concerned about it right now. Just realize this curve exists. You just can't see it. And that's why we have to admit that we can be wrong. We have to admit that we can be wrong. So we can be wrong. We can be wrong because if we land down here, right, it's more likely that it's on this curve, for sure. But there's still a chance that it's up on this curve. And if it's on this curve, and we say it's not, we've been wrong right here. We've been wrong right there. Is that fair? Is that fair? If we say it's changed, that means we believe we should be down here. But it might still be on this curve. That's a type 1 error. You say something has changed when in fact it hasn't changed. That's type 1. That's saying, you know what? We're so far to the left of this curve, it doesn't belong up here. That's a correct statement to say, by the way. But you could be wrong. You say, to hell with this, I think we're down here. But you might still belong up here. It's just that you got one of those goofy outlier data points. Totally fine, totally fine. Fair enough? Fair enough. The other way you can be wrong is the false negative. Remind me again what a false negative is. Remind me again what a false negative is. Nothing changed.
But it maybe really did.
Well, I'm going to put two words in front of nothing changed. You say nothing changed, but in fact it did. Is that okay, darling? I love what you just said. So in other words, to simplify it down, to dilute this down, I think this helps for learning it. A false positive means you say something changed when in fact it did. You say something changed. You say, we're way off the chart. Something's different. Well, no, not necessarily. You could be wrong. A false negative is you say nothing changed. So you landed over here somewhere. We're back on Paris's null curve, which I love that you just said that, Paris. All your p-values are based off your null curve. So, you landed over here. You landed over there. Nothing changed. I'm in the confidence interval, right? I'm in the confidence interval. Could you be wrong?